What's up, y'all? Hope you had a good week. For me, it was all right. Got a little bit of work done. Got plenty of sleep. It was nice. A less hectic week than usual, which is good. So this week, we're going to kind of branch out a little bit. Last week, and in the previous 2 weeks, basically, we've talked about translation, linear translation. So translation means like moving through space left to right or up to down, forward and back. This week, we're going to talk about the analog for rotation. So we're going to talk about how rotations occur. All right. How rotations occur, what things drive them, etc. So this is all about rotations this week. There's a lot of new symbols, like new letters that we write, right? But a lot of the intuitions from linear momentum will carry over. So there's going to be, like I said, a fair number of new symbols, new equations, but they have really convenient metaphors in linear momentum. So a lot of our intuition should carry over all right. Okay, we do have a lot of ground to cover, so let's hop right into it. Okay, so in this first part, it's the intro. I just want to introduce a couple of the basic sorts of questions we'll be asking, what kinds of quantities we're going to be looking for, and finally, give you a little bit of verbal intuition for where we're going. So these will be the ways that we'll be describing rotation. We'll quantify the rotation rate. We'll talk about how the rotation changes and quantify that, how the rotation rate changes. And finally, talk about causes of this, quote, rotational acceleration, the causes of these changes in rotation. So that's what we're building towards. This will give us an overall theory of how rotations occur and how they start and how they stop. Okay, so a couple of basic principles we'll use in words. We're going to build up to these again, but just to have them in words in our back pocket, is that objects rotate at a constant rate unless acted upon. So this is similar to an object staying in motion unless acted upon by an outside force, like a constant rate of motion unless acted on by an outside force. Similarly, if I just started a top spinning on a surface that was frictionless, then that top would keep spinning forever, right? It would never falter, just like inception. So if I start rotating something, it only stops rotating when I act upon it somehow, and it's going to be called torque. If it's torqued, if there's a torque acting upon it, its rotation rate can change. All right. And another thing that is a little less intuitive, but I wrote it down anyway so we'd have it just from the get-go, is that changing the rate of rotation of an object by some amount takes more force the closer you are to the pivot point. The pivot point being the region that stays at the same point in space as I rotate. So for example, what a pivot point is in this scenario is, if I've got this pen and I start rotating it, okay, my pivot point would be like the center of the pen. This part that's not moving as I rotate it. If I rotate it around this axis, then I have a pivot axis, if you like, a pivot point, like say here. It just keeps rotating around that point. That point stays at the same position in space, even though this little part of my pen that I can use to clip onto my pocket protector or whatever, this part is now moving, right? So there's a point that doesn't translate in space. That's what we call a pivot point for any rotation. We're going to get a little bit more rigorous with pivot point in the next one. Okay, so a couple of useful quantities. I mostly wanted to just put these all up front so that as we go through these equations, you have something to refer back to. So it could be a good idea if you're watching this live to just write these down or take a screenshot or whatever and kind of push them onto the side. Or if you have access to the PowerPoint slides, you can just download them if you like. So we're going to use these 7 variables. So to describe rotation, we use 4. We use the angle, which describes exactly at what point in a rotation my pen is, say. How far around the circle, so to speak, is my pen. We're going to use omega, which is the angular velocity. It describes how quickly the thing is turning. We use I, the moment of inertia, which we also call rotational inertia, which describes how hard it is to slow the thing down in its rotation or speed it up in its rotation. The larger the moment of inertia, the harder it is to speed it up or slow it down. And L, the angular momentum, which is, for now, we'll just call it the angular equivalent of linear momentum. The important thing about angular momentum is that it's a conserved quantity. So if I looked at the whole universe, the angular momentum of the whole universe is pretty much constant. It should be exactly constant. At least that's what we're saying here at this point in physics. Okay. Changes in rotation rates. There's a few ways we describe changes in rotation rate. This one, it looks like a tau, like time constant, but it's not time constant. I want to separate that off the get-go. Tau is torque now. It's a vector quantity. Tau refers to the basically the angular equivalent of force. So it describes the way that I cause rotations to accelerate or decelerate, the way that I cause rotations to increase in speed or decrease in speed, decrease in angular velocity to be more precise. All right. R is the displacement from the pivot point. So again, the pivot point is the point that doesn't move, say, in a typical rotation, the point that doesn't move, like that doesn't translate around in space. So R refers to a vector drawn from that pivot point to another location in space. So for example, just to throw an example down here, say that I had a seesaw. The seesaw is a classic example in physics. I have a seesaw, boom, boom, okay? So where I would typically like to define my pivot point is the point that is stuck in space. So as, say, I put a mass on this side of the seesaw is going to pivot down, right? So the seesaw is going to pivot down. As it pivots down, I'm going to draw the downward pivoted one in a slightly different color. Boom. So it pivots down. As it pivots down, this point is kind of pegged in one place. So my pivot point, PP, is right there in black. P dot P, cool. All right, and a displacement vector R is just something that's drawn out from that position. So typically what we're going to do is we're going to draw out a displacement vector to some point where a force is applied. So here, the mass falling on my what do you call this thing? Falling on my seesaw. A mass falling on my seesaw is going to cause a force, right? When it hits the seesaw, they're going to interact. It's going to cause a force. So typically, I would be interested in drawing a displacement vector that goes from my pivot point to wherever the force is applied. Okay, we're going to see that a little bit more later, but just know that displacement vector means starting at the pivot point and then going out to somewhere on the thing that's rotating, going out to some position on the thing that's rotating. Okay, and of course this vector R is described by some numbers, right? So like for example here it might be like, I don't know, 3, 1. R could be 3 in the x direction, 1 in the vertical direction, something like that. Okay, and the last thing is force. Y'all are familiar with force? Again, say that this thing is pivoting. I will just go ahead and draw it for fun. Then I would have a downward force generated by the mass's interaction with the, there we go, force of gravity. Mass's interaction with the seesaw. So as the, or really it's a normal force, I guess, at that point. But the point is, there's some force acting on the seesaw that's causing it to pivot. That force I usually denote with a little arrow, as in a free body diagram. Okay, I think that's it for this first video. Again, just kind of getting us used to a couple of the ideas that we'll be carrying forward and trying to build up a little bit more rigorously and pulling along these quantities. So again, because it's a bunch of new like vocabulary, like in terms of new Greek symbols and such, I recommend just having this on the side. It'll make some of what I say later a little bit more intelligible. Okay. All right. Thanks for joining me for the introduction. I'll see you in the next one.